Here is exercise 3. In the exercise above, we use the superposition theorem since there are several independent sources. You may doubt how to use the superposition theorem here since there's only one voltage source here. Here we use the homogeneity property of the linear system. If the current I is 1 ampere, the voltage here is 2 volts. Then the current here is 2 amperes. According to the KCL, the current here is 3 amperes. The voltage here is 3 volts. According to the KVL, the voltage is 5 volts. The current is 5 amperes. According to the KCL, the current is 8 amperes and the voltage is 8 volts. According to the KVL, the voltage here is 13 volts and the current is 13 amperes. According to the KCL, the current is 21 amperes. The voltage here is 34 volts. What does this mean? It means that if the voltage source is 34 volts, the current I is 1 ampere. Now the voltage source is 51 volts. What's the corresponding current I? It's a simple linear relationship. 51 over I equals 34 over 1. Then we get I equals 1.5 ampere. If you don't solve it in this way, you will find that it's difficult to solve it by the series and parallel connection of the resistors. One ohm connects to 2 ohm in parallel is 2 over 3 ohm. It seriously connects to 1 ohm is 5 over 3 ohm. It's complicated to solve the following series and parallel connections of the resistors. Once you get the equivalent resistance seen from the left to the right, you have to solve the following current divider circuits to get the value of I. It is too complicated. It is a very effective way to solve the circuits by taking advantage of the homogeneity cleverly. At the end of this lecture, I have 2 notes for you. The first note is that the superposition theorem is only used for the branch variables, that is the branch voltage and current, not for power. Power is not the branch variable. We use this simple circuit to explain. We need to solve the power absorbed by the resistor R. We use the node voltage method to solve the problem. This is a reference node. The node voltage here is U. Then we get 1 over 1 plus 1 over 1 times U equals US minus IS. U equals 0.5 US minus 0.5 IS. Since the resistance is 1 ohm, I equals 0.5 US minus 0.5 IS. Due to the associated reference directions, the absorbed power PA equals the square of 0.5 US plus the square of 0.5 IS minus 0.5 US times IS. You see, the absorbed power isn't the linear combination of US and IS. It is a nonlinear item. So it isn't equal to the algebraic sum of the absorbed power when US and IS is 0 respectively. You must keep it in mind that the superposition theorem isn't suitable for calculating the power. The second note is that the dependent sources don't take part into the superposition. We've discussed this point at the beginning of this lecture. We take this circuit as a counterexample. This is a series connection of 3 elements. We need to solve U. It's simple due to the KVL. US equals U plus 0.5 U, so U equals 0.667 US. If the dependent source takes part in the superposition, the solution is like this. When US takes effect alone, U prime equals US. When the dependent source takes effect alone, U double prime plus 0.5 U double prime equals 0. So U double prime is 0. You see, U prime plus U double prime isn't equal to U. So when we apply the superposition theorem, we regard the dependent source as a energy or signal processing subcircuit. In other words, it's an element in the linear system, not a excitation. So the dependent sources don't take part in the superposition. Okay, this is the end of this lecture.